All right, so we can begin now. So we have Amihay agreeing to speak for us. Thank you very much.
Yeah, so I'm going to raise this topic of what is known in physics as weak duality. Deal with refers to the company. Comes with some parameters that are not so
Maybe use that. That would be here better. And then recording at least.
yeah, well, this is low.
Well, it'll be better for the recording. I don't think it'll help Chunhao right now, but it'll be better for the recording.
Okay. So this notion of a coupling is specific for the physical setting of equivalent gauge theory, and it doesn't play much of a role in the geometry. And but the way I would phrase it in a mathematical way is that I have a pair of quivers Q1 and Q2. And they satisfy the relation that the Higgs bunch of one is equal to the Higgs bunch of the other, and the Coulomb bunch is equal to the other. Okay, and what we will do is to give a set of examples, and we will show some techniques of constructing families of such cases. There are infinitely many in such cases, and so one can study about the suspects. So the first example that we will take will go under the name of program accidents. No one equivalence, and it goes like that. So we start with quiver 1n, and that, and it is known that the Coulomb branch of this is the A.
This is an eraser.
Line singularity of type A, which we denote by a capital letter. And the Higgs bunch of the same quiver is the minimal important orbit of SMA.
Right.
Okay, so this is known. Another thing which is known is that the work of there's no
that should hook. It's so it should go okay.
out. So from the work of Gaff and Kochesky, they tell us that if I take C1 here, well, this is so we use here an extension of the quiver where we allow for the gauge node to be of type SP. So C denotes the element of this quiver, and D here refers again to the algebra, so it's the algebra of type D. We sometimes use the notation SU2, and SO2. Like that.
Mhm.
So for the work of Klaff and Pochesi, they propose such a quiver. They tell us that the Higgs function Higgs is the singularity, where here this label refers to the minimum topic of SO2. Now, it is you could take this equivalent to the Coulomb branch, and you find that it is of type D line singularity. And now I use the low rank equivalence, and I use the first equivalent we found. By the way, all of the examples that I'm telling you now are well known to the physicists over here. So you could ask any question. You could ask them for any questions.
Okay.
And so here I have this the first pair. I take Q1 to be 1, 4. And Q2 to be C1 D3. And then I satisfy this equivalence. And so that's the first example. It just follows from the low rank accident that the D3 is equal to 8.
All right, yeah, D3 is equal to A3, I guess.
Okay, so have a look at this. Tell me if you have any questions.
I guess this could be considered an accident. Or usually we start D at
So,
4. For
They
these.
they have different, you see that they generate different families, but because of this special value, you could get this equivalence. Now, in terms of the equivalent data and the computations that we do, they are quite different.
Right, yeah. Yeah, the gauge theories are not the same, but it's true that D3 equals A3. I mean, in terms of the classification, we just can start D at 4, obviously, but in the context of this general thing, it makes sense, especially as a 3, and then you get 2 different theories of the same.
Yeah. Okay, any questions about this part? We are going now to extend it to more general cases, but we'll use the same low rank equivalence.
Why is it called weak? It's because this weak is somehow related to a Higgs and Coulomb branch.
So the typically you think of the Higgs functions computed at weak coupling and Coulomb branch and strong coupling. And so because we have equivalence of Higgs function to Higgs function, that's so this field is weakly coupled. We're going to compute it, but it's just a moment map equation. So the fact that I'm using moment map equations map let's in the point that there is weak coupling.
But then since we're also asking for the Coulomb branches, it doesn't mean that we're asking for both weak and strong coupling then.
So strong coupling maps to strong coupling. Weak coupling to weak coupling.
Weak, strong.
Yeah.
But you just don't to say strong.
So long.
Weak, strong. WSS.
Also in 3D mirror symmetry, we don't refer to this thing, we just say 3D mirror symmetry. And the thing is that when you have a mirror pair, then the weak coupling of one is
The strong coupling of the other.
Yeah.
Although I guess that when you talk about 3D mirror symmetry, you could ask more. Some people just want that, I guess, and other people maybe want more from that.
But with reference to the coupling.
I mean, I guess when you say 3D mirror symmetry, it could be asking for more than just something to do with the Higgs and Coulomb branches, I guess.
Like informations, computation.
Maybe something about the gauge theories themselves, like in 2D mirror symmetry, you have some what do they call it? 2 different topological twists, 2 different twists of the differential or something to get the 2 different theories. You could ask for a relationship like that, right?
Yeah, there, when you have a topological quick twist, you remove completely the determinants of something, and so this question becomes this terminology of the root of sum is not relevant.
Okay. But in 2D mirror symmetry, still the A and the B sides are somehow given by two different twists of the differential, yes.
Yeah.
So I guess this is supposed to be true in 3D as well.
The twist, yeah, the twist will just remove the dependence of both in two and in three dimensions.
But I thought that one can say that the Higgs and Coulomb branch can be interpreted as coming from two different twists of the differential.
Yeah, you could do that.
In which case, I guess
It follows from
you're setting the coupling by choosing the twist.
yeah, it's not a mysterious thing. I mean, a symplectic singularity has sister action, which in many cases in the physics setting is source of an SU2.
Right.
Right. Now the twisting is just taking the symmetry of space-time, which in the geometry doesn't have much. Right? And we remember that field theory is a collection of marks between space-time, which is three-dimensional and two-dimensional, right? And the symplectic singularity. Right? Now there is a map. There is a SU2 symmetry here, SU2 symmetry here. The twisting is just taking a diagonal side.
Okay.
Now I can do it once for the SU2 which lives in its branch, and once for an SU2 which lives in a Coulomb branch. This will give me two twistings. Okay. So let's say I have 3D here. And I have a mark for symplectic singularity, symplectic singularity, right? And there is an SU2 here because of the symplectic singularity. There is an SU2 here, which is just an extension of the rotation of the mark. And the twisting is just a mix between the two. Now, when I have a quiver, I have two symplectic similarity, as Higgs and as this will continue for the one. And then, so I have two SU2s. There is an SU2 Coulomb branch. There is an SU2 Higgs branch. And so the twisting is just taking objects which transform under each of them and looking at the ensemble. However, this has no mention of the couple. Just game playing with taking diagonal sums.
I see. So this is just that, but nonetheless, when one says that two theories are in 3D mirror symmetry, one can ask, I thought, some relationship that we interchange the result of these two twists. Somehow, the two theories, it sends one twist of one to the twist of the other.
Yeah, Imperial symmetry would exchange those two.
Those two, yeah. Exactly.
And therefore, I exchange one twist by the other.
Exactly.
I take the diagonal something between this and this. And under the Imperial symmetry, come out with diagonal something.
I see, and I see each other singularities here.
And just what people do is to list all of the different objects which from the ball and show how the parts can transform under the diagonal something. That's the first.
Okay. But a priori, if we take a supersymmetric gauge theory, and in order to extract its Higgs or Coulomb branch, you put on some differential or something, then at the end of the day, after you've done all that, you only have the data of the singularity and this SU2, then I guess is what you're saying.
Yeah.
There's no more data left. Okay. All right.
Okay. So the next set of examples will come from different topics. So I think what we are looking here is a example. And this has the same algebra as SU6. And I'm going to list all the partitions of the four in order to get new components. So these are the partitions. And there is a corresponding partition of 6, which maps to this. And here it's going to be 5, 1. Over here, we are going to have 3, 3. This will be 3, 1, 1. And this one will be 2, 3, 1. And 1, 2, 5. Okay, so there is a correspondence between those two algebras. There are 5 nilpotent orbits, and the partition notation for SL4 is this partition notation. I suppose that we know about nilpotent orbits. Now, using this, I can follow graph and Puchesi and write down quivers for all of those cases. So I'm going to take the quiver with flaming 4 for this one, 2, 1, 4. There is a relation between this notation and the partition. What I do is I take the transpose, and the differences are giving me the real numbers.
Right.
Okay? So this case I will have 4. And over here I will have 1, 4. And this will be a trivial. So this is the graph purchasing data for SM. Any questions about this?
So this is
The fixed ones of those quivers will give me the corresponding information.
so you have this prescription for going from a partition to a quiver, what you say.
So
And here you're always putting the framing of 4 on just one vertex.
yeah, okay. Now, there is also a Coulomb branch for each of those quivers, and the Coulomb branch will be the following the Lustig-Spaltenstein duality. So if we place the Hasse diagram in the given tone, and by Capocesi the Higgs branch of this quiver is the slice between this orbit and the trivial orbit. Then the Coulomb branch of this that's Spaltenstein duality, they tell us that we need to transpose. So I need to, for each node here, I need to take the node which is reflected by this axis here. And the Coulomb bunch will be the Coulomb bunch of the transpose. Right? It's going to be the slice of the transpose. In this case, the Coulomb bunch turns out to be the same thing because the transpose of this is this, and the transpose of this is this. And I get that this quiver is self-zero. Let's do this example. So this case, the X bunch is in slice between this orbit and this orbit. I take the transpose of this is here, transpose of this is here, and so the slice between those two orbits will be the common bunch of this.
Right.
Okay. And so I have those squiggles give me the slice and also the slice of the transpose.
What's the prescription for going from the partition to the quiver?
Let's take, in fact, we use the transpose. So this has the partition 4, the transpose is this.
1, 1, 1, 1.
The differences are,
The differences are there.
yeah. And then let's take this one. So the differences are 2, 1, 1,
Oh,
which is the transpose of this.
oh, I see. Okay. The differences. Okay.
Okay.
Yeah.
Simple prescription. And again, going back to Cappuccino.
Yeah, yeah, definitely, definitely, yeah. And now if you take the transpose, you have to take a different slice. Yeah, I guess you, in the type, and at least in the type A case, you can get a magnetic quiver, but I guess you're not interested in that at the moment. That's that.
Well, not at the moment.
Okay. All right,
Okay.
sure.
Next thing I do is I can take 3 of those and I can combine them. For example, I can take this way. I have 3 to 1. Like that, I take 3 of those. I take 4 here. And then another 4 here. 3 to 1. And another 4. Yes, I'll take 3 tokens of this type. And this one right here. Now what I do is to take all of those 3, combine them into a single node, such that the resulting quiver will be 4, 2, 1, 1. And 2. Okay. And I can do this by taking any number of quivers like that. I can take not just 3, I can take several. And the common feature is that they all have this framing 4. I can collect all of them together and take the all framing nodes and turn into a single gauging.
Right.
Okay. So this is gauging that are.
Yeah, you can do that. Yeah.
Okay. So by this construction, I can get infinitely many figures because I could choose n legs. And I could,
sure.
Each leg will have one of those 4. This one will not give me anything interesting, even though one can try to look at some of the cases. But I will certainly get four options that I can use for this structure.
For sure.
Okay, now, so this is the construction, these are called structure funerals, and they have been studied to some extent.
Definitely.
Okay, and by the way, your colleague, which was here last week, may have spoken with this.
Ah. Oh, yes, yes, he did speak about them in a little bit, yeah, but not this, not exactly, what you're saying, but yeah, he spoke about them. He was interested in the, he was interested in connection to character varieties. Every month surface.
Yeah, so then it would be interesting to see with his construction. So I suppose the assigned structure variety pairs star shape. And I wonder if he thinks about those as building blocks.
No, I don't think so, but yes, it's a valid point of view, of course. I guess you can, this is something like this fusion operation, called fusion operation.
Yeah.
Mm-hmm.
Okay, so this is the construction, and that's also the reason why I needed those squiggles. I take those squiggles and I identify them with the model spaces of the atomics and so on these slices. And I take this set, I construct this foundation. Okay, so now I'm going to repeat the story. But instead of taking the algebra, let's say 4, I will take the algebra, so 6. And now, Graf and Pochesi give me different results, and here you have please check the answer 6 guys. So I will make a proposal, and you tell me if this is the correct one. So for this case, I will take the following quiver. So now these quivers are all of the Nakajima type quivers.
Mm-hmm.
And the quivers for SO6 will be just like this one, a set of alternating symplectic and
Can you just say again what the thing statement about the star-shaped quivers?
So at the moment, I have a construction, right, that's given an algebra and a set of microton topics. There is a corresponding graph Pochesi quivers for the A-type quivers. And using these A-type quivers, I can construct a star-shaped quiver. So now at the moment, it's construction. No statement yet. And in order to make the statement, I will have to repeat the construction with SO6. Okay. So for SO6, I will have the following quiver. I think it's C2. And the following will be and this one, I will have the partition 23. So the transpose is to Q. So I get 3. This one, I will have a here question that things will have. One choice will be yeah, which one? E1, E0. Yeah, so that's a problem. Even E1 or C1 E0. let's take this one. Now, the last one will be C1. C1 and D3. So I have the four quivers, which are the analog of those four. Okay, and I can now repeat the construction. I can take any of these four. I can take several copies of them, combine them just like in here, and construct a star-shaped quiver. Okay. And the claim is that the star-shaped quiver of type D3 will be, let's call it quiver 2. Quiver 1 is what we had before,
Mm-hmm.
with the same map. Yes. That's the star-shaped quiver of type A3. And I make sure that the same data is picked, right? So if I pick 4 legs type 4, then I should pick 4 legs of type 1. Okay, and so I will use this map to construct the star-shaped quiver. Again, infinitely many such star-shaped quivers. And they satisfy this relation. H1, H2, H1, and so
Oh, I see.
one. Okay, so this is the state. Now this is the non-trivial statement because I have, using these two constructions, I create very different quivers, but they have the property that each bunch of one is each bunch of the other.
Basically, you have this correspondence. Just because SL4 is isomorphic to SO6, you have this correspondence, so you can not only say that these individual orbits have to be isomorphic for the different quivers, the ordinary one and the orthosymplectic one, but now if you fuse them together and form arbitrary stars with corresponding branches, they still have to be isomorphic. That makes sense.
So it does fall under this the family of low-rank equivalence.
Right.
There is a particular case, which is the let's do the affine 7. Take the quiver from the family 7. And put here. So this is a special case of taking 2 copies of 4 and 1 copy of 2. Okay,
Mm-hmm.
as you can see here. So I can now construct the quiver, which is in SO6. I have a central node of type D3, and you have C2, D2, 1, and the same thing on the other side. And the 2,4 gets mapped to this one and so on. And what we can do on the board without much effort is to do the dimension count. And so here I have the dimension, the sum of these numbers is 18. This is the Goldcoxeter number of 7. And the minimal important topic of V7 is of complex dimension 34, which is one less than this number times. Okay. And you could now add these numbers over here. I have 6, so 12, 15, 17, that's 17. And the Higgs bunch of this is the line singularity type 7 for both of those. And the Coulomb bunch is the minimal important orbit of the 7. Okay.
The instruction, and you also have loops.
Yeah, I think it will be just the same, right? So we could add loops here from the A type, and we could add loops from the B type. Loops from the B type will correspond to this just a joint representation, and then it's just the business and family facing the equivalence.
We have a group of the statement, the weekly. We'll do that kind of really on the right lower corner.
I don't know, it's the joke is that this is a fifth year. But a group of actual I don't know, that's an interesting question. Certainly, we shouldn't really take it as a conjecture. And the big foundation, something is the whole foundation.
So what's the conjecture you say here? The conjecture is that those hold if
I construct Q1
Mhm.
by picking a collection of legs
Mm.
of vessel 4.
Ah,
I take Q2 by picking collection of vessel 6
right.
of the precise legs that map. And the slate looks at the projection, these function 1, function the other, and function 1.
But this from Higgs branch, this should just follow from the fusion construction, right? You have all these legs, they're all isomorphic, and then the group acting is isomorphic, and then you take quotient by the same group. So it should be just follow from fusion construction for a Higgs branch, I would think.
Yeah, because you're gauging the 6 or the 4.
For a Coulomb branch, then one has to say similar thing, but maybe one can also say the corresponding thing for fusion. For Coulomb branch, it's a bit different, obviously. It's not the Hamiltonian reduction of the individual legs, it's something dual to that.
Yeah.
One has to try it. For a Higgs branch, it seems easy, no?
It's possible that rather than look at this one,
Don't know, it's possible.
maybe
So it's going to be talk.
Oh, yeah, maybe, yeah, we can see about that, and maybe it's related to Ben's talk this afternoon about gluing Coulomb branch, just fusion and things.
Including extra, Ben's talk was about adding an extra function. The way we would think about it is process theory and just add another function that gives away to describe that. Maybe.
We will
he's
see.
doing partial intelligence. So the partial intelligence will be of type starship.
Yeah.
Alright, I didn't see that they look at the specialties. Because they don't do, they are only doing the A type. They don't look at the other cases.
What is this 18 and 17 again? Let's see.
So the sum of numbers is 18.
Ah,
The 72.
oh, I see. Well, it's not the same sum.
Yeah, but that's a well-known thing. Okay, there is an overall 6,000 which actually in this case. Here at best you could take
Oh, I see. So, but doing this fusion operation should have the Higgs branches equal, but you're saying that the Coulomb branches are not actually equal, they're just equal up to a product with some.
When we look at such figures which are unframed, we always take the convention that the unframed 6,000. And then we pretty much for that. So the last piece.
Ah, I see. And then they're equal then in that case. But then the numbers, the reason why the numbers don't add up is because of that C star then. Discrepancy, I see. So in the top example, if you unframe that C star, you turn the middle node and from a GL into an SL, that's what you're saying, then the two will have the same Higgs and Coulomb branches.
Yeah.
I see. Okay. That makes sense, yes. Very good. Okay, so this is, yeah, so I think this is, this will be worth thinking. We'll see whether the talk of Ben is related to this or not, but I think that for Higgs, it should be pretty easy to prove this conjecture, and then we have to see it with the.
It won't be related for a simple reason that is only going to consider A type two.
Oh, I see, okay.
So,
So for the A type, maybe this is related, but for the C and D type, I see, but this is a problem also for defining Coulomb branch. It's kind of the mathematical construction for non-cotangent type is harder to understand.
yeah.
Right. Okay, perfect. Yeah, this is very good.
Okay. So this is one family of cases. Now we'll do a couple of examples. Next case is not in the family of low rank, so we are going to move to a different family. And this time, the computational trick that we use is to look at different interests. Take this family. Okay. And I'm going to ask for 3 and this family brings two 3 one which is photosynthetic and the other one which is so claim that the following program. And there are in total, I have n plus 1 nodes. including this one. So I have entries for nodes. The nodes which are, that take away this one, I form the thinking diagram for the BNRG. Okay,
Mhm.
and here I have claim this was tested several times. Let's go to T1. 2. Six, 1. 2, 1. Any question about this? This quiver shows up in the work of Henderson and Pepper. Okay. This is a well-known term from there is and here I again need the help which they also split it here. So let's write Q3. And Q3 will have mostly linear. We'll start with Q1. And it goes up like that up to okay. Here I have a P0. P0 stands for so P0 has the trivial algebra. The corresponding gauge is O1, and we should take a look at the acting as a Z2 on the parameters which are associated with this H. And then I get K and continuous argument with that with K and CK. And it's a symmetric group. And in fact, this will be your multiplication. The first one.
Maybe we go down to 4.
Yeah. Down. And the total number of nodes is how much? On the line. On the line, I should get 2n minus 3. Any questions?
So this is again applying the same thing, and now CKDN. This is not applying the low rank anymore now,
It's not going to be.
but it still works. So
Yeah, so then there will be a correspondence.
now you have B. Are you calling it B instead of D?
What do you say?
B, because it's an odd dimensional, so you have a B there.
You can do simple examples. But that's a correspondence.
Okay, but why did we get this correspondence again? Where did it come from?
So Q1 and Q2 form a mirror term.
Mm-hmm. Ah,
Q1 and Q3 form a mirror term.
oh, I see. You have two different ways of taking mirror. Let's see.
And as a result, Q2 and Q3 will satisfy this solution.
So you have two different ways of taking the mirror of Q1, the same.
Yeah.
Why do we have two different ways of taking the mirror?
That's this follows from some extremely good structure. But we probably not have
Do you have a brain construction of at least one of these?
Yeah, for this we'll have to discuss orientable planes.
So for the orientable brains, you take this orientable according to corresponding to the Q1, and you apply S duality,
Yeah,
and then and then which one do you get then? You get the Q, and then if you apply the S duality to the orientifold for the CKDN, which one do you get then? You get the Q3 this way?
one I get through all 5 planes, the other 4.
Ah,
I don't do this model.
I see.
So we could discuss, if you really want to know when you are constructing.
Well, I mean, at some point, we don't have to do it now, though. I just wanted to know the idea. So basically, you're saying that there's two different ways to apply S duality. Is that what you're saying?
To read these quivers, two different ways to read these quivers.
Two different ways to read the quiver.
There are 2 ways of reading the 2 quivers. One from O5 plane, one from O3 plane.
Oh, I see.
And then once you get the quivers, you have a conjecture. And you could test the conjecture by computing explicitly the Higgs function to the function.
I see. But somehow, the bottom line is you take the Q1, you take its brain system, you take its S dual, and now you have a new brain system. Now, starting from this new brain system, there's 2 different quivers you can write for it. Is that what you're saying?
You insist on using this one.
Well, I don't insist. It's just that since you write that there are 2 mirrors. Yeah, but that's how you go from Q1 to Q2 or Q3, right? No, you don't.
I have a root of the quiver.
Okay.
One is from O5, one from O3.
Okay, but you start out with something for Q1, and then you have to get from that to Q2 and Q3. So there's just, okay. But from O3 and from O5.
One construction for O5 and one construction
For O3, I see. Doesn't have anything to do with brain system then.
So,
Okay, all right. Okay. Fine. We'll learn about that later then.
yeah.
But you don't need a Q1. Now, in principle, then you don't need a Q to start with a Q1. You could just start with any orientable brain system, and you might have 2 different ways of constructing quiver.
So the general statement will be that given a quiver of this type, if there exists 2 ways to construct it using brain, then I will get
Well, I see there's 2 different ways of constructing Q1 using brains. That's what you're saying.
that's the key.
And then each of these ways gives you a different if you like, magnetic quiver or whatever you want to call it.
Yeah.
Okay,
Essentially, it's because there are two ways of constructing magnetic fields for P-type, one of which is based on these diagrams, the other one which is based on field chains.
oh,
And, the diagram constructions are there for certain corresponding to slice that you're doing, sort of those ideas. The orbits high and the diagram construction fails. It's basically the position of the one there. Slide that up to the 2K node, or slide it beyond.
okay,
These were the sequence of orbits based on these two node electric.
okay. Okay. All right, well, we will have to discuss this in more detail later, I think, so otherwise the mathematicians won't understand. I think I understood everything until this bottom corner, left corner
Of the,
of the board, yeah. But now this new example, I will have to discuss more later.
Yeah.
Right.
and now, so this is a two parameter family. I have two labels U, K, and N. And so I can construct this family. Construct this family. They satisfy the relation. So again, I can take it as a convention. That the these values. So for this example, we said that this follows from logarithmic duality. For this family here, it just follows from the string instructions. So using such string constructions, I can come up with a collection of again projections, two pairs of quivers, where they satisfy this image. Okay.
And all of these examples will be the mirror of some particular quiver, or you can do ones that don't come from a mirror.
Okay, so let's do something which doesn't come from zero.
So it doesn't have to be the two magnetic quivers for some electric quiver. It could be
It's
more general.
the ingredient which is guiding is that there are two alternative constructions, regardless of whether there exists a mirror.
Okay.
In this case, it does. But now I'll give you an example where the level of the mirror. So we are going to take the family.
Could you have also cases where both the thing and its mirror have two different construction? I guess this could happen too, right?
We will have both. I just cannot think of such a case.
Okay.
It will certainly be interesting to explore it and find more examples. So the next case will be this family of equations. So it's a slight variation of this. And I'm going to take one time the family of windows. And here the number of nodes is just as you count. I have two pages here. And three The base K equals to, 2, gives me, normal space, which is H, to the power of n. And the base K equals to 3 is, minimum 8. Like that. The closure of the minimum 8. And, all other cases can, some spaces with. Then, if I can, so this is the quiver 1. And now we take quiver 2. Following time, I'll have a quiver which looks like this. So we go here the ends. Now we think and there's going to be long legs, so we go down in details. This thing is okay. And going down the legs, you take this one, you take this one. All the way, other image here, the same thing. Just like it's like that. And in this guy, I will have a C1. So this quiver fits into the family of the star-shaped quivers. Well, now, instead of taking the algebra D3, I'm taking the algebra DK. And here I have 3 legs. There is a long leg, this corresponds to the top orbit in the corresponding algebra. And this one will correspond to the minimum component. By the same construction that we have with the SOC. Construction generalized way of doing the SOC. And again, we have this projection, it's punch 1, punch 2.
Mhm.
And a special case is the case of the minimally 6. So now I have 2 types of quivers. One is the calculus case here, the calculus case here, and they give me the minimally important here.
I see. You don't have a mirror for this one. This is,
These are those
but you're still getting this E8. It's similar somehow to the example we had of E7 before, I guess. But
it's
now,
very close to the so this so now I can ask the question, given this family, I can ask what happens if I take this D3
mhm,
and change it to NBK,
mm,
and again use this long leg here, and I keep this one, C1B. And this will give me an additional projection for the pair that satisfies this.
I see. I see. And this example also comes from branes. And you take a brane, you have the same brain
Yeah,
system. You can
this
read it
time
in
it's,
two different ways.
It's instead of 03 and 05, I take 06 and 08. Once I construct with 06, once I construct with 08.
Okay,
When I construct with 08, I get this. When I construct with 06, I get this.
08 up there and 06 down there. I think.
08.
Yeah, 06, okay. Perfect. Amazing.
Okay. And let's do the final example or family of examples. That's the E7 case. And for the E7 case, we solve this pair. And I'm going now to take B and J here. Let me first write down the limit. So we get 1, 2, all the way up to 1, 3. Okay. I have a K here. One.
Mm-hmm.
And so that's equal to 1, equal to 2. Will be a generalization of this. So, so as a special case, K equals to 2 is the minimally 7. K equals to 1 is another. K equals to 2 is 7. Equals to 1. Equals to 1 is H to some power. In Q2, we look like a central node of P. Okay, so this is quiver 1, quiver 2. Then central junction.
Amazing. And all of these come from stringy construction.
Yeah. Yeah, to explain if you really want to look at the string constructions, So this example comes from topical geometry. So there is a topical geometry construction which I don't think we touched so far with very webs.
Mm-hmm.
And we could just apply the techniques and get the once this figure, once this figure. And that is nice in this.
Brain webs, you say you can.
Yeah.
So you can use stringy construction or brain webs, you say. It's the same thing.
Subset
Of stringy construction. I see, and that's the kind of one that you use for these. But this one over there was not the brain webs, and
this thing here.
the example there, that was not from
This
brain.
is you could already do it in, so this one is completed using 3, this one is completed using 5, and this results have arrived in 99,000.
Okay. But when you say brain webs, what's that referring to? It's just the.
So here we use 03, 05. In this case, you use 05, 07.
Mm-hmm.
And the reference to brainwave is that you form, you use topical curves. This is the main, the simplest topical curve.
Oh, I see.
And we construct a web, a brain web, in this case. But this will have not discussed. I don't remember any. So I couldn't introduce this.
So given a tropical curve, you can produce some kind of brain web. And
There is a map between the brain web and the collision. And I can do it once with the unitary nodes, like here, and once with
mhm,
and that's how I will get the
I see.
right, so.
And in this example also, looks like this one was not a brain web. You said this was something simpler, you say.
Yeah, it's so still constructions allow you to evaluate the different brains participate, and each time you pick a different one, you get different families of fields. And that's the reason we're able to generate more computer.
But from a tropical curve, you have a construction of brain webs, you're saying.
So a brain web is the physics name for a topical curve.
Oh, I see.
It's just synonyms. The topical curve, if you look at the definition, satisfies the same definition.
And from a brain web, you can get a quiver, say.
Yeah.
And maybe more than one quiver.
If you fix the brain web, then
You get one quiver.
well, so if you fix the brain web, you could get 2 quivers. It's going to be the molecular quiver and the
Right. But now you can get more than one brain web. To get 2 different quivers, you get 2 different brain webs.
because I'm using here the different types of construction that going back to this case.
Mhm,
So take this particular gauge tool.
mhm.
We started using 2 different brain systems. Once the O3 and once the O5. The O3 will give you autosymplectic numbers, and the O5 will give you the
Mhm.
and that's how we get the curve.
Right.
And I repeat the same trick for the case of those 2 examples.
Yeah.
And then I get again once the unitary tool, once the autosymplectic. Unitary tool.
And each of these go by way of a brain web, though. Here.
This would be from brain web.
Mhm.
This would be from a system of D6, D8, O6, and O8.
Ah.
D6. D6.
So only the one on the bottom comes from a brain web, you say.
Yes.
Given any tropical curve, you can have a quiver associated to it, then, is what you're saying.
Say it again.
Given any tropical curve, and you can have a quiver associated to it, then you say. Because it's a brain web, you see.
Yeah, with some conditions. I mean, the brain ones are not fully understood. So, since you were in general, if you could say yes.
Okay, but where does the K come?
Some brain words that I can just start the quiver for. And can precisely say which ones it's difficult.
But where does the K come into this tropical curve then, at the bottom? I don't see a K involved in tropical.
So, it's similar to what you have.
Yeah, but you just wrote a tropical curve with just this three, very simple tropical curve with it.
It will be very
It's
similar.
like
to
it.
this.
Mm-hmm.
It will be very similar. I start with such a quiver.
Mm-hmm.
Once I can construct it using, let me write this down. So once I can construct it using D3 and D5. And for this guy, I will add a 5 plane, and for this guy, I will add a 3 plane. Okay,
Mm-hmm.
and in fact, I just repeat this thing, I just change the brain system. The quiver, this starting quiver, remains. If I do it with this and D5, I get this thing.
Mm-hmm.
If I keep this and do with the 6 D8, I get this thing.
Ah,
And if I keep this quiver and take the 5 D7, I get this thing.
ah. But these ones, but in the original case, you had that this was a magnetic quiver. This Q2 and Q3 were magnetic quiver for Q1, but now these are not supposed to be magnetic quiver for Q1, right? For the original Q1. Even though
they are magnetic quivers, but they are not 3D mirror.
they're not 3D mirror, you see.
Yeah, so here they are 3D mirror,
Uh-huh.
here they are just magnetic quivers, but they are not 3D mirror, because we don't have the other side.
What?
I can give you two, to satisfy such a graph. They won't give you one side, say that.
Ah. So when you use D3 and D5, somehow you can get this relationship for both Higgs and Coulomb branch. When you do these constructions, you get one relationship, you see.
Yeah, like this example contains the rate, and we know that for a single queen, find the rate using diagram,
Mm-hmm.
and it has a Coulomb branch and Higgs branch. Now I cannot construct another quiver such that these relations will be reversed.
Okay, but what's the relationship with what makes these magnetic quivers for that original CK at the end? What's the relationship? Yeah.
I need to take a special limit, which is not a geometric limit, therefore I cannot explain it.
Ah, so magnetic quiver doesn't have to mean that you have a relationship between the Higgs and Coulomb branch. It's something more general.
It's more construction of a symplectic singularity using Coulomb branch.
Ah,
So that's also the reason I do not want to use S duality, because S duality necessarily implies that you have a free zero, but not always I have it.
So using the Coulomb branch of Q1, you can somehow construct these things, is what you're saying, or all of these quivers you somehow construct from Coulomb branch of Q1.
Yeah, the reason I cannot explain it in the geometry is because there is an additional parameter which I mentioned at the beginning, that's the pH coupling.
Mm-hmm.
This doesn't have a geometry in the context of the geometry.
I see, but somehow there's this Q1 is associated to some gauge theory, and then there's some construction to go from that to these gauge theories associated to these quivers here. Is that the point?
Say it again.
So is the statement that you have the gauge theory that produces quiver Q1,
Yeah.
and then there's some procedure for going from that to gauge theories that produce these
Yeah.
quivers.
Yeah.
Okay.
So I take this starting point, I construct a system, and what I do is I construct
Okay. Any questions? We should probably have lunch soon. Are there any questions? This is very interesting. There's lots of examples. I don't understand the mathematics behind these new examples.
Yeah,
Any questions?
yeah, we could go over construction of the light systems.
Yeah.
We need the equivalence.
Yeah, we could do this. We need
We'll
to,
take some.
we'll take a few sessions. Yeah.
Cases for the 60, so the so. So it's the two that the origins like
Yeah.
I just want to show us there's no way to go between the two. Or they're really two separate constructions.
You could say the same thing, it's really the same thing as here, so you want to say those words, let us say. In other words, once I will construct it with one, once I will construct it with 6. Did I mention how to use the points?
No, I don't, but I just want you to see if there is something.
It's just this. So the symplectic theories, symplectic ratio, have two types of constructions, and we keep on using it in all of those three examples. That's behind this. It's here, and it's here.
Two different constructions. You mean the O5 versus O3, or D6 versus D8? But,
O6 versus O8.
but you make it sound as though you can apply all of these different constructions to the same original thing. It's just that if it's O5 and O3, then they produce the same symplectic singularities. But if you do D6 and D8, they produce the same symplectic singularities.
Yes.
Or D6 and O8.
It's, I really need to change between, well, let me just show you, and then before this on the screen.
Okay.
Let's start with O5.
Mhm.
I take O5 mounts, I take a noise,
Mhm.
and I take 2K
Yeah.
D3. And I take N D5. This is giving me the concept.
Mhm.
And alternatively, I will use and I don't use 2S and
D3.
both of them give me a construction of this quiver.
What, even though you're doing orientifold in a different place, you get the same quiver, you say?
Yeah.
Okay,
And the next thing I do is to change those labels. Right? I had O5 and B5 and this. B5 and this. And this.
mm-hmm,
And I can do just the same by replacing the O5 by O7.
ah, but all of these different things, all these different things will give you the same quiver there on the left.
Same ring system, and when I read the quiver, I will give those different values.
But there's one way of reading the quiver that gives you that original one on the left with the DN and CK.
One way,
That's what you see.
two way system.
Each brain system that you're writing gives you this DN CK quiver. Or gives you these other quivers,
Yes,
depending on how you want to.
yeah, because
Yeah.
every brain system has two quivers I can write down. One is an electric quiver and one is an electric.
Which could be related by S duality, it doesn't have to be.
It could be only from this case. When I
Okay.
use three to five elements.
Yeah,
Any other setting, I don't have this in.
I see. So this O3, you don't have S duality for that. But you can still, it also does. Mm.
Still, 3, 5,
Mm-hmm.
3, 5 minutes.
Mm.
But when I get to other cases,
So these ones with the,
yes, this was 3. I have this 3,
mm-hmm.
label my 3, and there's no.
I see. And all these examples with the D6, D8, O6, O8 use the same. Also the same brain
Same
system.
brain system, I just changed the name, but because of the dimensionalities, the way I read the quivers changes.
Okay. Dimensionality meaning what? What's your orientifold
I
line?
changed
Oh, you change P. So you do change the dimension of the brains,
yes.
but somehow,
And also
Up to-
it changes the dimension of the field theory. Instead of 3-dimensional theory, I have 5-dimensional theory.
so it's not, S duality doesn't always apply, but you still have two different ways of reading the quiver. One that gives you this one and one that gives you that original one.
Yes. One
But-
gives me the split, the other one gives me anytime. And then I get this.
Okay. Okay. Well, okay, so we'll have to discuss this some more. Shall we break for lunch then? Any other questions before we do that? And I don't know if we will be able to come back to this room because we probably will have to let it. At 1 there'll be another lecture. But at 2 o'clock, we have Ben Webster speaking online. So we can all get our lunch and maybe we go into the physics room or some other place until Ben's talk.
Yeah, we don't have a setting for
Oh, yeah, so for Ben's talk, I don't have a room reserved at the moment to watch together, so we're probably all watching on our own.
so maybe we should just watch on our machines.
Yeah, I think this is what we're doing for Ben's talk. I didn't reserve a room for his talk. I thought it would be more convenient for everybody to have their own. But we can all have lunch now, and then his talk at 2. So let's thank Amihay though. Here.